You know, the AI models we have today are absolutely brilliant conversationalists. But let's be honest, they're essentially blind, just living inside a world of pure text. So what happens when we finally give them eyes? Well, a groundbreaking new paper just laid out a blueprint for what comes next, and it might just flip everything we think we know about building intelligent AI. So that leads us to this massive question. What if the next huge leap forward for AI isn't about getting better at talking, but getting better at actually understanding the world it's talking about? Right? I mean, how do we build an AI that doesn't just describe a video of a ball falling, but actually starts to grasp the idea of gravity itself? That's the real mystery this research is trying to crack. And the big idea here is so simple, it's brilliant. They're saying, look, let's stop trying to just bolt eyes onto a pre-trained language model. Instead, let's go right back to square one. The researchers decided to train vision and language together from a complete blank slate in a super controlled experiment. They wanted to find the real, fundamental rules for how these two senses should learn together. And what they found, well, it was this incredible synergy, but also a critical imbalance that nobody had really put their finger on before. Okay, so if you want to get clean answers, you've got to run a clean experiment. The team basically set up this amazing investigation to isolate exactly what is going on when a model learns to see and read at the very same time, without any of the baggage of already being an expert in one area. So how they actually do it? This is the clever part. First, they used a framework they call transfusion, which is this smart combination of learning methods. It uses diffusion for vision, which is amazing at generating images, and the standard next token prediction for language. Then they took these totally fresh, untrained models and just fed them a rich diet of videos, images, and text. The key, and this is really the most important part, was starting from scratch and comparing all the different versions. It made sure language didn't have some kind of unfair head start. And here is the secret sauce that makes this whole thing so legit, something called isoflop analysis. The best way to think about it is like a weight class in boxing. It makes sure that every single model being tested has the exact same amount of computational power, the same training budget. This way, you know you're actually comparing the intelligence of the architectures themselves, and not just who had the bigger or more powerful computer. It makes it a fair fight. All right, so the experiment's running, and as the researchers started digging through all the data, 4 really crucial clues began to emerge. And together, they start to paint a really clear picture of how multimodal AI actually works. So let's break them down, one by one. So clue number 1 is all about how the AI processes what it sees. They found that this one specific method, the representation autoencoder, or RAE, was basically the perfect visual translator. What it does is it learns to squish an image down to its absolute core essence, and then it can reconstruct it perfectly. Think of it like the ideal internal system for sight. It lets the AI be both a brilliant art critic, understanding what's in an image, and a brilliant artist, able to create totally new ones. Now, this is where it gets really, really cool. The second clue uncovered this incredibly powerful synergy. See, when you train vision and language together, it's not a simple case of 1 + 1 = 2. It's more like 1 + 1 = ×3. The visual data actually helped the model get better at language, and the text data helped it get better at vision. They feed off each other, making the whole system way smarter than the sum of its parts. And this idea leads perfectly into the third clue, the emergence of what they call world modeling. So get this, without anyone explicitly teaching it physics, the model just started to get it. It began to understand concepts like object permanence, that things still exist even when you can't see them, and basic cause and effect, just from watching videos and reading descriptions. It was building its own little internal model of how the world works, which is just a massive step towards real understanding. And the last clue points to the best way to make these models bigger and more powerful. The mixture of experts, or MOE architecture, turned out to be the smartest way to scale up. So instead of having one giant overworked brain trying to do absolutely everything, MOE creates a whole team of specialists. You've got your language experts over here, your vision experts over there, and this lets the model scale up way more efficiently and effectively. But out of all these clues, there was one discovery that really stood out as the big revelation, a fundamental, deep imbalance in how AI learns from seeing versus how it learns from reading. Honestly, this is the major plot twist of the entire research paper. So here is the absolute heart of the matter. Vision and language do not learn at the same speed or even in the same way. Language is pretty efficient. It learns well, and it mostly needs a lot of model capacity, more brain power. Vision, on the other hand, is an absolute data hog. It is incredibly data hungry. To get better, it needs a tidal wave of visual input. It needs more eyeballs constantly watching the world. That imbalance is what they call the scaling asymmetry. And I mean, this chart just says it all, doesn't it? Just look at that difference. To get the same little bit of improvement, vision requires vastly more data than language does. And that creates this huge bottleneck problem, right? How are you supposed to build one unified model when its two main senses have such completely different appetites? And here it is, the solution. The mixture of experts architecture just elegantly solves this whole problem. Remember that team of specialists we talked about? Well, Mo can dynamically assign resources where they're needed most. It can give the language experts all the high-capacity brainpower they need to think deep thoughts, while at the same time letting the vision experts drink from the massive fire hose of data they're so thirsty for. It just perfectly harmonizes that imbalance. It's the perfect fit. So, what does this all mean for the future? Well, these findings are way more than just some academic curiosity. What they really give us is a clear, data-backed blueprint for how to build the entire next generation of AI. Let's just put it all together. This research gives us a clear road forward, beyond the text-only models we have today, and towards true multimodal agents that can actually perceive, understand, and act in the real world. It's a massive foundational step for an AI that can develop real common sense. And it proves that MOE is the key. It's the most efficient architecture to scale these unbelievably complex systems. This paper is basically handing a roadmap to the entire field. Now, of course, we gotta keep a level head. This is one major study, and it uses one specific framework. And those world modeling capabilities they saw, they're still in the very early stages. So this isn't the final word on the subject, not by a long shot. But it is a huge and really well-supported first step in an incredibly promising new direction. Which really just brings us to the final big question. This research gives us a blueprint for AIs that can see, read, and start to build their own internal model of the world. So, are we finally actually on the path to creating an AI that has genuine common sense? I'd love to know what you think down in the comments. Thanks for checking this out.